Welcome to this new video. We'll continue our studies on tensors. So, in the last video, we talked about the components of a tensor, right? In trying to explain them. So, for instance, let's look at this: TA equals to B. So, T is a tensor. T is a tensor. A and B are both vectors, right? Or more scientifically, or the way the mathematicians write it. Yeah, so they are both vectors. So previous video we talked about the components of tensors itself. Now we want to talk about the components of this transformed vector B. Remember, A is like the origin, like a vector, so it's been transformed to B by T, which is a tensor, right? So A is being transformed with respect to WRT, respect to this, right? Good. So if we have A as A-I-E-I, explicitly that is A1 E1 plus A2 E2 plus A3 E3. Now this is familiar to us already by this time. So B equals to TA, right? So T, we can substitute this A, the A above, we can substitute this one into this. So it's T A1 E1 plus A2 E2 plus A3 E3. That gives us A1 T1 E1 plus A2 T. Sorry, we don't need. There's no one here. Yeah. So A2 E2 plus A3 T E3. Good. This is one expression you should always remember. Tij. From the last video, you remember seeing this, right? Tej. If you remember what this expression is all about, is like this Tij is the component of the tensors equals to the dot product of the unit vector, that's the original vector, then the transformed one, right? So that's one expression you should always remember. We'll be needing it very soon. So this B, now if you look at, let's look at things in a more realistic or practical way. This B, it's something like this: B1, B2, B3, right? Yeah. So it has components which are B1, B2, and B3. These are the components of this. And these components, yes, which is a scalar, sort of, right? They're just, since there are terms just in it. Yeah. So if we have B equals to A1 T1 E1 plus A2, no, we don't need a T1, sorry, I keep writing T1. T, A T E2 plus A3 T E3. So to find B1 will be, look at this closely, A1 E1 TE1 plus A2 E1 dot TE2 plus A3 E1 dot TE3, right? Now, it's still, that is this B1 is still equal to, we want to find, this B1 is a component, right? And how we get that is like the unit vector, the dot product with the complete one. So that's this B and EI, which is basically E1, E2, E3. So this is just a component B1. So for B2, look at this very closely again. E2 dot TE2 plus A2 E2 dot TE2 plus A3 E2 dot TE3 equals to E2 dot B. Similarly, for the third one, should be A1 A3 dot TE1 plus A2 E3 dot TE2 plus A3 E3 TE3 equal to E3 this. So B1 B1, B2, B3 are all components of B, right? So it's as good as simply putting all this in that vector itself. So if you remember, coming back to this expression, we used that in the last video, right? So from this expression, we can further simplify B1 to be T11A1 plus T12A2 plus T13A3. B2 to be T21A1 plus T22A2 plus T23A3. And for B3, you can further simplify this to be T31A1 plus T32A2 plus T33A3. So all these are just the components of B, right? So if you call this star 1, right? So if you look at, now let's see how we can put this in matrix form. B1, B2, B3. So we can single out T1, we can single out T21, T31, T12, T22, T32, then T13, T23, T33. And it's assumed that if you're multiplying by a vector, that's A1, A2, A3. Peradventure, let's assume if you don't understand what just happened, if you look at this, let's take the first, multiply row by column, right? So it's T11 times A1 plus T1, that is T1 times this. So let me just do that here. So T12 times A2 plus T13 times A3. If you look at this exactly, this is exactly what is here, right? Good. So similarly, you do for the other two columns. That will give you an idea of the transformation of what I just did. So this is it in matrix form, right? Then also that's explicitly stating the components, right? So this is T. So what we've just done basically, we've just simply, if you look from here, from B equals to TA. Oops, sorry. Equals to TA. We moved from here, this point, to this point. Right. Now, of course, this is still normal algebra if you look at things in perspective, right? So what makes index look, index, what makes index notations is that it saves you lots of space and time as long as you know how to manipulate what is needed. So by the Einstein's notations and the explanations I've made, Einstein's notation and index notation are the same. So by understanding how to manipulate this, you can simply write out expressions like this without stress. So let's quickly go back to this. Now, let's use the index notation to write out what we've just done. A equals to AI, EI, right? A is the vector. This is components of it. TA, if you're doing the transformation, it's T AIEI, right? To still give you AITEI. I just simply rearranged it to have the components of A times the transformed components. Now, look at this is what we're trying to solve or trying to write out explicitly. This. Now let's rewrite this. BK equals to B dot EK. Now, this is the component. Sorry, this is the vector itself. This is the component. If you can remember, we did this here. See when we're writing this one, right? for you to find a specific component, you multiply by the vector or the unit vector in that direction, right? So it's E1, B1 equals to B. So similarly, we are doing the same thing here. Yeah. So for the vector, so yeah. Oh, sorry, this I interchange this. Right. So this is the component, and this is the vector itself. Right. The vector is B. EK is like the unit vector in that direction. The unit vector here in that space. So as we've done previously, we're able to get B1 equals to B dot E1, B2 equals to B dot E2, B3 equals to B dot E3. So basically, we've used that same terminology to get this. I hope this makes things clear. So this is the component, and so for you to get the component, you find the dot product of the vector itself and the unit vector in that direction that you want that component. So bk is equal to b dot ek. B is equals to ta, right? Yeah. So you replace that with ta dot ek equal to, if you look at here, we've already gotten ta to be this, right? How do we substitute ai? Okay, now what I'm trying to do is I'm trying to make sure that I don't have a conflict of units. A conflict of index, right? ej dot ek. Yep. So if you look at this closely, I'm simply writing this one is this, but I substituted TEI equals to TJIEJ. If you remember what I've done in previous lectures, this is some of the J's, so the I is valid, right? And if you look at the other side, we have an I too, an I. So this is tenable, right? So BK is equal to AI TJI EJ dot EK. Yes, I think you can pause the video if you need to understand exactly what I've done, but I'll try my best to explain and make things very clear. So from here, TA equals to, the component form, right? Then you rearrange this just to make things easy. So when you rearrange it, AI is component of A's, TEI is component in that direction. So if it's a unit in direction, in direction of E1, that unit vector, you have TEI. Then TEI itself, right, means this. This is an expression for TEI because this is the component. We've gotten this expression in previous notes, right? So TEI equals to this. This is the component of the vector, the component of the transformation vector, or transformation tensor, or the tensor itself, right? The tensor times the unit vector, right? To give you the transform, that's the new one. So we've moved from EI to TEI, which is this. So we're just trying to play with it. It's simply maths. We're trying to develop an expression for this. So AI TJI, this, yeah. So this can further be simplified to BK AI TGI. Now if you look at this, the chronicle delta JK. If you can't remember how we got this, you just need to look at previous videos. See how we got that. Yeah. The chronicle delta, if you can remember J, this, if it's 1, if I equal to J, if I is not equal to J, then 0, right? So yeah, let's simplify E, the dot product, we get this. Now if you further want to simplify this, BK equals to AI. Now if you want to simplify this to see from this expression, you should be getting TKI. right? Sum on the j's is off, then the ik, ki, right? Get this, yeah. Then if you look at this, both expressions must agree in both sides, because if you say these two sum on the i's, then you have a k here. So yes. So in a compact form, we've not be able to resolve bk is equal to tki ai, right? So if you look back at this expression we've gotten here, this one, this expression, that's basically what this has been written as now, right? Or even this one, or even this one, or even this one. So you see how we've moved from writing it in this, how to write it in index notation, right? If you try to expand this by the normal rules of I equal to 1, 2, 3, k equals to 1, 2, 3, I bet you'll be getting an expression same as this in star 1. So with index notation, it's been made very easy. We've gotten this expression. Index notation, indicial notation, I know any of such terms, I usually hear any of them. Right? So I hope this is clear. Let me quickly do an example. I think that will throw more light to what, to some certain level of transformation. So example 1. So if you have a tensor, let's say a tensor T. The work of a tensor, as we've known, is to transform, let's say transform the base vectors it has, EI, right? Transform them, E1, E2, E3, into another set of vectors, right? 2E1 minus 6E2 plus 4E3. It transforms this one to 3E1 plus 4E2 minus 6E3, and transforms this one as 2E1 plus E2 plus 2E3. So what has happened is that E1s have been transformed to TE1s by a vector T, by a tensor T, right? So now the question is, how does this tensor transform vector A equals to EI plus 2E2 plus 3E3? Now, previously, when solving questions like this, if you notice, we simply did this, right? We just found a T. We transformed the unit vectors from E1 or base vectors to TE1. But now this question goes a step further. After you find T, notice how does this tensor transform the vectors? So after you get your T from there, you find a TA. So after you find it, you now see how does you get the T to give you a B, right? So previously, we got our T's by, if you just simply look at the transformed base vectors, right? Simply looking at it, 2 minus 6, 4, 3, 4, minus 1, then minus 2, 1, 2. So this is the tensor that does the transformation. Now we already have A, right? So to find B will be 2 minus 6, 4, 3, 4, minus 1, 2, 1, minus 2. B, then A should be 1, 2, 3. Just, in case someone is probably not getting how I populated this matrix, let me just quickly explain that. We're transforming from E1 to TE1, right? And this is done by transformation matrix T. How we got T from this is this. We look at 2E1 minus 6 and this. So if you look at this matrix, 2 minus 6 and 4. For this one, 3, 4, minus 1, minus 2E, minus 2, 1, and 2. If you really need to understand the details, I suggest you watch the last 2 lectures or so to give throw more light on that. So to find b in this case, you're going to be multiplying the transformation and the transformation vector, which is the tensor t, and the vector a. In this, well, if you do it by your normal calculations, let me see, you can use a calculator, but 2 times 1 plus 3 times 2 plus minus 2 times 3 should give you 2 plus 6 minus 6, 2. Yeah, the next one should be minus 6 times 1 plus 4 times 2 plus 1 times 3 equals to minus 6 plus 8 plus 3 to give you 5. Then 4 times 1 plus 1 minus 1 times 2 plus 2 times 3 give you 4 minus 2 plus 6 will give you 8. So you can use either hand or your calculator. I mean, your calculator makes it faster and you are sure of not making computation mistakes. So basically that's what B is. I hope this makes sense. So previously we only found a particular value, and we only found the t, which was its tensor, but now we now apply the tensor to a vector to give us another vector b. So let's go over tensor operations. I believe this should be pretty straightforward, especially if you've done a linear algebra class before. Right. Well, let me slide this in case you still need to look at that. So for addition, so if you have tensor, T is a tensor, S is a tensor, belong to tensors, let me write it like this. Let's say that's tensors, right? Then A belongs to the class of vectors. So T plus S A equals to T A plus S A. That's your distributive property. Distributive property. I hope I got the spelling. That holds. Then, if you add two tensors together, you should get B, W. W also is a tensor. This, of course, I mean, the dimensions should agree, right? That's common sense, basically. Plus Sij in indicial notation should be this, right? These are the components here in indicial notation. So for you to write the component of Tij, it should be Ei dot Tej, right? It should be Ei, and yeah, you can still use I, Ei dot Sej, right? To give you Eit plus Sej. I hope that makes sense. So in matrix form, W equals to T plus S, or matrix notation. So that's pretty straightforward for your addition. For your for product or multiplication, so then if you multiply, it's still the same as this, right? And if you do STA, it's still the same as ST and A, right? Yeah. So let's look at components of T of S. Let's look at its components. T of S. T of S Ig equals to EI dot T of S Ej equals to EI dot T of S Ej. I hope this is making sense. Then EI dot T of S. Now let's use MJEM. Yeah, so you have to take care when using the notations so that we can split the S to become SMJEI TEM equals to TIM SMJ. So T of S. So this just shows that I've used this to prove to you that T of S matrix form is same thing as just multiplying your T and your S, right? And similarly, if you multiply your S by your T equals to S and your T, right? Now, don't be tempted to think T of S is equal to S of t. No, it's not equal. That's because tensor product does not have a commutative property. It's not commutative. I hope this is clear. However, it is associative. So if you have T, S, V, they belong to a class of tensors, right? So all these expressions hold. If you multiply that, you have three tensors. If you multiply them, the order really doesn't matter. They'll give you the same value. If you have this, then if you decide to, let's say, multiply with a vector at the end, it's still the same as, it's the order doesn't still matter too. That holds. This still should be equal to this. If you have S outside, then V of A, that should work. If you also have T of S, if you have T of S, VA equals to T, if you multiply by the S multiplies this first in bracket, then you cover with this, that holds. So basically, that's tensor operations. If you are trying to square, if you multiply T by T, that's fine. If you have Q, T, 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 that holds too as well. Those are valid tensor operations. Okay. Now let me solve an example. It should be example 2 for this place. Yeah. For this example, so let's assume we have a rigid body. A rigid body basically is a body that undergoes little or no deformations. Yeah, either zero, quite slight, or maybe infinitesimal deformations. So let's assume let's assume we have a tensor R, right? Tensor R is a tensor, or R. And now there's a rigid body, right? This rigid body, we're going to rotate it 90 degrees. Rotate with 90 degrees right hand. That's right hand rotation, right? That's right, using the right hand coordinate system about axis x3. Our axis is like this. This is x3, x1, x2. So we have a tensor R, and I'm going to do a right hand rigid body rotation about x3. Okay, let's take a look at what's happening. So when we do a right hand rigid body rotation about R, so let's find R, that tensor. So what is R? Of course, R is a rotation tensor. R is a tensor already, as we've been saying, right? Now let's see what happens. So if you rotate 90 degrees, this is x1, right? Rotate this 90 degrees, x1 becomes on this point, right? Let's see E1 here, E2, E3. So E1 is here. If you rotate here, becomes RE1. Because if you 90 degrees, right? From here, you move 90 degrees to this point. Yes. Then E2 is here. Right? If you rotate by 90 degrees, it moves to this point to become. Okay, I think I would have used the different colors for the rotated one to make things easy. So you can easily see what I'm doing to make this RE2. RE1 here, right? RE2. You're rotating about E3. It says, yeah, so this E3 remains the same, right? It remains the same because we are rotating about. It remains the same. So in clear terms, how we write it should be this RE1. So RE1 has now become E2 because you see it moved from here to this point. It became on the same line as E2. RE2, right, has become this. Look at this. How do we describe it? RE1 is pointing in the positive direction. E1 is pointing, so RE2 is in the negative direction, so it can be said to be E minus E1. Hope this is clear and makes sense. Then RE3 remains itself. So the rotation tensor R is basically, if you remember what we've done previously, this is like the previous example, 0E1 here, 0E3, 0E2 plus 0E3, 0E2 plus 0E1. Just make sure you don't mess up the order, even though it looks like I wrote it randomly. Let me take that off. It's misleading. But I just wrote that to make you know that there are zeros for the components that are not explicitly stated. So so the right thing should be 0, 1, 0, minus 1, 0, 0, right? Then 0, 0, 1. So this is rotation tensor, right? So when you rotate about the x3, rotate 90 degrees about the x3 axis. This is the x3 axis here. 90 degrees, E1 moves to this point, then E2 moves to this point, it becomes negative of the E1. Okay, now let's find another tensor. So part B of the question, let's find another tensor, S. S is a tensor, right? So S belongs to this. S is a tensor, right? So S is going to rotate, is 90 degrees right hand rotation too, but this time the rotation is about the x1 axis. X1, X2, X3, E1, E2, E3, right? So if we can see this, so we need to get the transformed part E2 as E3. So this one does not change because this is where the rotation is about, right? This doesn't change because this is where the rotation is about. So this becomes this still remains E1. It says 90 degrees right hand rotation about x1. This is x1. This does not change, so it's E1. About E2, it says 90 degrees about E2. So this S2, this E2 rotates to this point. It rotates to this point to become SE2. So here is E3, right? Because E3 is not exactly on the same point. Because here is 90. How do I draw this? But here is still 90. From this point to this point is still 90. I hope that makes sense. Then X3. Then for this E2. Oops. Okay. So for this one, E3, it moves 90 degrees too, right? If it moves 90 degrees, it moves this way. So to give you negative E2, because E2 this is positive and this is negative, right? So this is negative E2. So to find for the rotation tensor or the tensor itself should be 1, 0, 0 because E1, E2 and E3 have 0 components. For E3 we have 0, 0, 1, right? Then for this part we have 0, minus 1, 0. So that is the rotation tensor or about axis x1. I hope that's kind of easy to understand. Okay, now let's try something. Now let's look at something like this. It says, let's find a matrix let's find a matrix of the tensor, right? That's or a tensor itself. That will be correspond that what it first does is rotates about S, then rotates about R. Part A has we were able to find a tensor R that rotates about x3, and part B, you find a tensor S that rotates about x1. So let's now find a tensor itself that does the work of both of them, right? A tensor that the first thing it does is it rotates, okay, let me use the right words, find that corresponds to the rotation S, okay, tensor that it corresponds to the rotation S, then rotation R. So basically it does the same thing, but it does because it does the S part first before it does the R part. I mean the R S rotation and the R rotation, right? So this is simply tensor products. That's all you need to do, right? So SR will simply be, it does the rotation S first. It does the rotation S then correspond to R. But the thing is, you don't write SR for this to be wrong. The rotation should be RS. So we substitute for the R's we have before 0, 1, 0, minus 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, minus 1, 0, 1, 0. And if this is computed correctly, we get, what am I doing? I hope I'm doing the right thing. Okay, it is, yeah. Yes, okay, yeah, that's right. So it will be 0, 0, 1, 1, 0, 0, 0, 1, 0. Now, if the question says the tensor that corresponds to the rotation R, then S, right? Then we know that what you're supposed to write should be SR, right? So you just simply write the same matrices 1, 0, 0, 0, 0, 1, 0, minus 1, 0, and 0, 1, 0, minus 1, 0, 0, 0, 0, 1. If you compute that correctly, you should get 0, 0, 1, minus 1, 0, 0, 0, minus 1, 0, right? Now, if you look at both expressions, of course, RS is not equal to SR. So you have to pay attention if you are trying to solve a practical question example, right? If you are rotating with one tensor, then rotating with another tensor, you have to know exactly what you need to do, basically. Yeah, I hope this makes sense. Now, what we started first by talking about a rigid body, right? Let's assume this is a rigid body, and a rigid body, its deformations are minimal, or let's use the word infinitesimal deformations, right? So let's, if you have a point, let's assume there's a point on this rigid body, and let's say this point has the coordinates of 1, 1, 0. Let's say it's x1, x2 points, and x3 points. Has these points. So if we rotate, this is a rigid body, right? If we rotate this rigid body, what is the new position of this point? That's the question. If we rotate this rigid body, what is the new position of the point? Now, if we understand something clearly, we can look at this that since the order, this is very vital, right? If you decide to rotate by, if you use the apply R transformation, R to transform first before the S, you get a different value if you apply the S before the R. Yes. So let's assume I want to rotate by R first. Sorry, rotate by R first, then S, right? So let's call this point R. So SR will be just simply be the multiplication. You multiply both of them, right, to get R dots. But if you want to apply S transformation before R, you'll get a different result, because it will be, let's say, the R prime equals to RS, then R. Now this is clear. So if you multiply this, let me just write this in slightly different color. SR we already have that from 0, 0, 1. I think that's where it starts from. SR 0, 0, 1 minus 1, 0. Okay, minus 1, 0, 0, minus 1, 0. Right. R, now let's look at R. R here is coordinates, so this makes R to be equal to 1, 1, 0. Look at it based on x1, x2, x3. So 1, 1, 0. If you simplify this, let's see, minus 1 is times, 0 times this you get minus 1. Or the zeros cancelled out, this should be 0, and this should be 1, right? So similarly for R of S, RS, if we look up 0, 0, 1, okay. 0, I think that's 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, right? 0, 0, 1. So you can see the position is different, right? Let's write it in more more in a decent form already. If you have this should, so R prime, now let's say R asterisk should be equal to minus E1 plus E3. R prime is E2. R prime should be E3, sorry. Hope I got the multiplication right. Yeah. Okay, here should be 1, I think. Yes, here should be 1. So the positions are different after rotation, and we apply the same transformation but in different orders. So this just was able to show to us that this are different. Hope this example did help. Okay, so to conclude this section, let me just quickly run through all we've done basically. So basically we talked about the components. Basically we talked about the components of the tensor. The components of the transformed tensor, right? So if we have a tensor T, we are transforming a vector A to get the transform vector B. So we're able to find the components of B, and we did it with a simple algebra. We had lots of long expressions, right? And came to this one, came to this point, and came to this point. They're very long, really. But with indicial notation, you see, it was quite short. And we're able to arrive at a simpler notation also. And if you substitute with all these values, you will get the same values you had gotten at this point here. Then we did an example of transformation. We transformed EI to TEI, right? By finding the transformation tensor, or linear transformation, which is T, right? Then we went a step further by applying T to another vector to get B, which we got here as this. Then we discussed about the tensor operations, the addition, which is distributive, the product as well too. And we're able to prove by the example that it's not commutative but it's associative. And we have different expressions to show that from this point All these expressions can show that. Then in an example, we're able to show what happens when you rotate and how the when you rotate with respect to the basis vectors, what happens, transformation and the values. So first we rotated uh, about this axis, the x1, for to get the r, and for s rotated about, sorry, for r rotated about x1, x3, then for s rotated about x1. So the rotation tensors were significantly different. You see, this was different from this, right? And also when we now apply them, if you say find a single tensor that corresponds to rotation about s, then r is totally different from a single tensor that does rotation from r then s, which we notice that these values were different from these values, right? Then if on that rigid body, we have a rigid body which we're considering, if you have a point on that rigid body, this point changes depending on the order of the rotation. And that was what we were able to prove with the values of r prime and r asterisk. I hope you find this video useful. The third part of the tensors will be talked about in the next lecture. We'll talk more about transposition or transpose of a tensor, dyadic product, and a couple of other too. Yeah, thank you.